Hello everyone. Today I'm going to talk about Simulink, Matlab Simulink environment. We are going to make a tutorial about how to use Simulink to simulate our power electronic circuits. Simulink is an extension of Matlab. It uses block diagrams and transfer functions and some fundamental blocks to do a multi-domain simulation. You can do a model-based design from bottom to top, from a very fundamental blocks to very high level and complex designs using Matlab Simulink. We can do a system level design, as I said before. You can construct blocks with the help of transfer functions. You can use the block diagrams, make necessary connections to construct a much bigger and complex systems. You can simulate the physical system. You can simulate the real physical systems like a wind turbine or a photovoltaic system or a high power power system with the help of Simulink. You can generate a code with a C or C++ code for embedded systems, for DSPs, with the help of Simulink. You can test and verify the constructed block diagrams at real time. This is a very interesting options of Simulink. You can connect a real physical system, for example, a power electronic device to your to computer, and do a hardware in the loop simulation where you where you take data and give data to the power device and control this device in real time. Simulink provides a variety of kinds, a different variety of libraries. Simulink is used in different professions. For example, it is used in aerospace applications, it is used in control systems or mechanical engineering. It is used in our department as well. It's used in power electronics or power systems area as well. So there are a lot of different toolboxes and libraries where it is very useful to use them. It offers block diagrams. You can construct your own blocks, your own transfer functions, your own blocks to use in simulation. It offers graphical editor where you connect and make necessary connections to these block diagrams, and it offers a different variety of solvers. For example, you can solve these simulations in continuous time, discrete time, or you can do a phasor solver. Now I want to make a tutorial about how to use Matlab to construct a boost converter. In order to do that, I'm going to open a Matlab which I installed at my computer. Our department offers a license to Matlab, but the problem with that license is that it doesn't offer all the toolboxes that we are going to use in our simulations. So you should either download a fully licensed Matlab, or you can use Matlab Simulink Online, where you can just Google Simulink Online and click and just log in with your MetaMail, and you can use the full version of Matlab Online with the latest version, of course. It's just similar. It's very similar to the installed version. It just uses cloud computing. I mean, if you don't have a very good computer, you can use this online tool as well. Now, but I'm going to use the version that I have installed at my computer. In order to open Simulink, you can do two things. First, you can just write Simulink to the command window where Simulink opens, or you can click Home, then you can click Simulink, and the Simulink interface opens again. Now I'm going to create a blank model, Now it's creating. Yes. Now we are at the Simulink interface, as you can see here. Now, first thing I want to mention is the libraries. You can access to libraries from this button. As I said before, Matlab library offers, of course, the full version of Matlab offers a different variety of libraries, as you can see here. I mean, there are aerospace and computer and control systems and so on. So, but the toolboxes that we generally use in our simulations is the first toolbox, this Simulink and commonly used blocks. We are going to use these blocks very commonly. And the other toolbox that we are going to use is the Simscape toolbox. Under Simscape, you can click electrical and specialized power systems. And this toolbox contains all the equipments, all the fundamental blocks that we are going to use in our simulations. There are electrical sources and electrical machines, induction machines and synchronous machines and DC machines and so on. There are diodes and MOSFETs and a lot of switching equipments. So we generally use these blocks in our simulations. You can either use this library browser to access the fundamental blocks, or you can just click on the blank point of the page and start writing the name of the block diagram block that you are going to use. It just searches whole libraries and offers you solutions. First, we are going to add a power GUI. Power GUI, as I discussed earlier, is a solver for which is used in Simscape toolbox. We should add this solver in our simulations all the time. Then I'm going to add a DC voltage source. Now, as you can see here, when I write DC voltage, it offered three different block diagrams, but the ones that we are going to use is the specialized power system, the Simscape block. So I'm going to choose this one. Now the amplitude of the voltage is 24 volts. As I said earlier, we are going to construct a boost converter, which is a very basic component in power electronics. And then I'm going to choose a switching device. I'm going to put a MOSFET in, of course, again from the Simscape toolbox. I'm going to add a diode here, this one. I'm going to add an inductor, but if you write for inductor, as you can see, Simscape doesn't offer an inductor because all the inductors resistances and capacitances are named as series RLC branch. You should choose this equipment to add to your simulations. When you double click on any component, there is a menu, there is a pop-up menu where you can change the parameter of the device. As you can see, I'm going to choose an inductive load which has a value of 250 microhenry. When you click to a component and push the Ctrl R button, the component can rotate. So it's a very, I think, important part of the simulation if you have an OCD or something. When you right click and drag, it just copies the same component. It's a very handy tool. Again, just right click and drag. You can copy the same equipment. I'm going to put a capacitor here, which has a 200 microfarad capacitances. and then I'm going to put a resistive load which is a 3 ohm resistance. Now we have put all the necessary equipments. We can make the necessary connections by simply dragging the mouse. Here to here and here. Now, as you can see, diodes and the MOSFET has this M port, which stands for measurement port. You can measure the current and voltage of the diode and MOSFET, but we don't want to do this right now. So I'm going to close all the measurement ports. And one thing that I want to mention is that you may not know how this component blocks is working. So as a side note, you can just click this help button, which opens a documentation which is prepared by Matlab, where you can get all the necessary information about this device. It says the input parameters and output parameters, and how should you use this block and so on. So it's a very helpful thing to click this button. It's a very important aspect of using Matlab Simulink, because it is used in very different kinds of applications. So there's a very wide range of users. So if you just Google the necessary phrase, you can just get any information about anything regarding Matlab. Now, one missing thing is the gate signal, so we should turn on and off this MOSFET. So there is no just a single way of doing creating a gate signal. So what I'm going to do is just click the PWM generator, search for a PWM, and I'm going to, you can construct these blocks by yourselves as well. As you know, PWM is just a salted signal with a reference comparator, and then you can create your own PWM signal. And I'm going to make this period of let's make it 10 kilohertz period of, yes. Sample time is this. Of course, I didn't set the sample time. Now we have put the power GUI in the beginning of the simulation, but we didn't set the required amount. You can choose the simulation type, the solver type here. Generally, we are using a discrete solver, because continuous solver takes more time than discrete solvers. So you can choose the discrete solver, and the sample time, you should choose a reasonable sample time. If you decrease the sample time very much, if you make it 1 nanosecond or something, it would take much more time, but the results would be very close to the continuous case. So it's just a trade-off between the simulation time and the time it takes to complete the simulation. So I'm going to choose a sample time this. And another thing to note here is that we should change the module configuration parameters from here to power GUI to be activated. We are going to choose fixed step. It was a variable step, and we are going to choose the discrete non-continuous solver, and I'm going to click OK. Of course, we should add a DC input to the PWM generator. Let's look at how this PWM generator works. As you can see, it takes a reference and compares with the salted signal, and it creates a duty cycle according to this. So I'm going to add a constant this constant is just gives this value from the simulation. I'm going to choose a duty cycle of 0.5 and I'm going to connect it to here. So what this block does is it creates a PWM with a 0.5 duty cycle at 10 kilohertz. And our simulation is pretty much done, but the problem here is that how can we know what's going on in this simulation? We don't make any measurements. We don't measure any voltages or currents in this simulation setup. So as we do in real test setups, we are going to put a voltage measurement. It's like a probe of a oscilloscope, and I'm going to put this voltage measurement to the output side to measure the output voltage, and I'm going to put a current measurement to measure the inductance, current of the inductance. I'm just going to delete this part and make necessary connections. It reads, as you know, current measurements is done in series and the voltage measurement is done in parallel. So we should connect the current measurement in series with the inductance. Of course, this diode should be rotated. Now we measured the current and voltage, but how can we observe the change with respect to time? In order to do that, we are going to put a scope. This scope, when we connect it to the measurement ports, it will tell us the voltage with respect to time. But I want to see both voltage and current at the same scope, so I am just connecting it to the same scope so that I will see the voltage and current measurements at the same time. Now our simulation is pretty much done. The last thing to do is set the simulation stop time. I mean, how many seconds will it take to simulate. I'm going to make 0.1 seconds. So I'm going to click run, and hopefully it will run without any problems. Yes, the simulation is done. When I double click to scope, yes, when I double click to scope, as you can see, both voltage and current measurements can be seen here, but it plots this both of the graph at both of the lines at the same graph. What you can do is you can click the layout and you can choose this. I want them to side by side, so I'm just going to click this one. So it just shows the output voltage and the output current on the bottom, output voltage at the top, and output inductor current at the bottom. But the background is black, so if you want to change the simulation style, you can just click view and style, and then you can choose the figure color as white, axis color white, and the line as black, so it's just more visual. You can change the thickness of the lines, you can change the color of the lines, and so on. I'm just going to make it this one blue. Now I want to focus, zoom in on this part. As you can see, this is the output voltage, then this is the inductor current. If you zoom in very closely, you can see that this is our actually the step time that we have set in the beginning of the simulation. If you increase this step time, it will be much more detailed, but it will of course take much more time. Now, in order to export from this scope, you can just print. You can use the print figure here. And that is all actually. Of course, you should note that this simulation is done in ideal case. We didn't put any series resistance or series resistance to the inductances or capacitances. We didn't put any forward voltage drop on diodes. We didn't put our own resistance to the MOSFETs and so on. We didn't include any parasitic, so it is just a very ideal case to simulate a boost converter. When you do your simulations, if you want to get as close as possible to the real results, you should add as much as information as possible to these blocks. You can just double click and add this on resistance and switching time and so on. So that is all in our Matlab Simulink tutorial. If you have any questions, as I said before, if you just Google it, you can find a lot of useful information about Matlab and Simulink. But if you are stuck in some part of the simulation or in your projects, you can just send an email to us and we will try to help as much as possible. Have a nice day.